All right, thank you for your patience as always. I know we end up missing the first couple minutes because of my class run over time. You've heard me rant about it before, not going to waste any more time. Reminders 5.1 and 5.2, that due date has already passed. So hopefully you were able to finish those in time. I know most everyone was keeping up with the homework. I think I might only need to have a chat with like one student. 5.3 and 5.4 were finished last class, so they are going to be due on the 10th. And you will notice I do not have 5.5 up here, which is the next section we're going to cover today. It's in a pretty extensive section that we need to cover because we're going to take a very, very, very slow approach introducing what the graphs of sines and cosines look like. But then the ultimate point will be able to generate those graphs, at least the basic picture, really quickly based on far fewer points than the number of points we're going to do initially. So we're only going to get through 5.5 today, and we won't even technically finish it, which is why the homework isn't listed as due in a week. However, per usual, if you finish 5.3 and 5.4, or once you finish those two sections, please go ahead and start 5.5. Go ahead and get done what you can get done so that way you'll stay ahead, because next class 5.5 is going to be assigned, and then the next section is likely to be assigned as well. We'll start talking about the test soon, but we lost a few minutes due to my class runover. So let's go ahead and pick up where we left off between sections, which means we will be starting 5.5, the graphs of sines and cosines. Let's go.
Graphs of sine and cosine functions. We are ultimately going to do graphs of all 6 trig functions. These two are by far the most important. I put a lot more weight into them in tests. You'll see more homework questions on them. The ideas of them will be used in later chapters, whereas with tangent, secant, and cosecant, their implications are more in a calculus setting. So we'll establish the graphs, but then we really won't come back to them again for the rest of the semester. As I always say, I'm very honest about what will keep being an issue and what is not. I'm not saying that the other 4 graphs are unnecessary things. I'm saying that they won't have as much importance in our course as they will in calculus. The importances will be when we want to establish the inverse trig functions in our course. We'll still need the ideas of what those graphs are, but we won't be redrawing them 50 times. Sines and cosines, you might redraw them 40 or 50 times. So these trig functions, we think about ourselves going around in a circle, but what if we actually wanted to plot the values of sine of 0 degrees, sine of 30 degrees, sine of 45 degrees, sine of 60 degrees against a vertical axis? As you keep increasing the angle, at what height would we be on a vertical axis based on what the cosine is? So the angle will be our argument, and then the x coordinate on a unit circle would be the output for a cosine, or the angle would be an argument for a sine, and the output would be the y coordinate on a unit circle. Or you can use your 2 triangles, which we'll do as well. So we will make the horizontal axis the angle theta, and the vertical axis the output of the trig function. But since we traditionally use x and y axes, we'll use these as the input and output variables. So instead of saying y equals sine of theta, we're going to say y equals sine of x. So this x right here is not the x coordinate on the unit circle. This is our theta. Again, we're using an x here because we're going to be graphing them on an xy coordinate plane. So this x is our theta, as I've just said, and the y would have been the output of the trig function. What just happened? Why did that pull up? And you probably didn't even see it pull up because it's a Zoom menu. So now X is the angle and Y is the output. I already said that. I just wanted to write it in a smaller notation. We are going to first create a super detailed graph to establish a much simpler version of the graph. So let's see. I'm trying to count. We're going to do like 17 points to make this graph. Kind of like when you first graph a parabola, you do at least 5 points. You do like from -2 to +2 or -3 to +3. Maybe 7 points for that second case, to establish that, oh, okay, well, after you see the X and the Y values, there's this symmetry and it ends up looking like this. So then later we just find out what the vertex is, we plot our vertex, and then we kind of draw it from there or from there. That's the idea of how we learn a simpler way to graph without just doing a giant, ridiculous table of values, which is what we're about to do. So we're going to take a 17-point approach and we're going to turn it into a 5-point approach. So only 5 of those points is going to be important for making the graph, but you'll have to have the shape memorized to connect the dots appropriately. And so that I don't have to take up the entire page, let's do a horizontal table of values instead of vertical. What I'm saying here is, instead of doing something like this, and I'm going to erase it, X, Y, instead of going 0, 1, 2, we're going to do it more like this. And again, I'm going to erase it, X, Y, 0, 1, 2. That's a horizontal table of values because we're going to have so many inputs. So X. And first, before I even write that, so graph Y equals sine of X. So we're having X and Y. Again, X is the angle, Y is the output of the trig function. Probably going to need this whole thing. And I will do this in degrees. You could do it in radians as well. And we're going to start at 0 degrees. We're going to go to 30 degrees. Then we'll go to 45 degrees. I hope I give myself enough room. Then we're going to go to 60 degrees. And then we're going to go to 90 degrees. So there are the 1, 2, 3, 4, 5 angles we will use established in the first quadrant. I mean, 0 and 90 aren't technically in the quadrant, so 2 quadrantals and the in-betweens. Then we're going to go to 120 degrees, then 135 degrees, then 150 degrees, and then 180 degrees. Sorry about the unevenness of the bottom links. Don't worry about that, please. I'm going to have to squeeze these in a little more, maybe. Let's see. After that is 210. Then 225, right? Yes. Then 240 degrees. Then 270 degrees. What I'm doing here is I'm getting quadrantals 0, 90, 180, 270, then ultimately 360. And then the 3 angles in between them that we can do with reference angles and those 2 right triangles. So 30, 45, and 60, those are all reference angles to 120, 135, and 150. They're all reference angles to 210, 225, 240. We're going to see a lot of the same outputs with plus or minus sign differences because we're going to keep going back to that idea. Then we have 270 to 300 degrees. Then it would be 315 degrees, 330 degrees, and finally 360 degrees. Sorry, I got a little squishy at the end. I should have started at the far left. I knew better. And I'm not even going to try and use my mouse to move that. Every time I do, it fails miserably. So we're going to find all 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. I was right. All 17 values, only using 3 bits of information. To fill the table, use the 2 triangles. By 2 triangles, I mean the 30, 60, 90, and 45, 45, 90, along with quadrantals and a smart trig class. That's how I'm going to fill this table out. So you're going to keep seeing me refer back to this stuff. These 2 triangles, a smart trig class because we're going to be using reference angles, but they all boil down to the original angle with just a sign difference. By sign, I mean plus or minus. And then for any of the quadrantals, we'll use the x and y coordinates as appropriate. All right. So for 0 degrees, that's a quadrantal. So we're talking about sine. Sine is always going to use the y coordinates when we're on the unit circle. It uses the y coordinates. So here's 0 degrees. This y value is 0, which means the sine of 0 degrees is 0. And I'm going to do the answers in blue. So again, this was a quadrantal. I went to the unit circle. I went here. I used the fact that sine is the y coordinate on the unit circle. The y coordinate 0 degrees is 0, so the sine of 0 degrees is 0. You could actually go ahead and fill out all the quadrantals if you want to just go ahead and knock those out. Let's do that. I think that might be convenient. So let's do 90 degrees next. So we're just taking the y coordinate. Why the y coordinate? Because sine takes on y coordinates on a unit circle. So for 90 degrees, the sine will be 1. For 180 degrees, the sine will be 0 again. It matches 0 degrees. But then the sine of 270 will be -1. So 90 degrees, it's 1. 180 degrees, it's 0. 270 degrees, it's -1. 1, 0, -1. 1, 0, -1. Now I also have 360. 360 degrees is the same as 0 degrees. They're coterminal. It's a full period of sine. So this one is the same as this one. Now, you want to know what's cool? I said earlier that we're going to take the 17-point method and turn it into a 5-point method. These are the 5 points you'll use. Using the quadrantals is the easiest thing you can do for yourself because the heights are nice and easy, like 0, 1, and -1. The rest of these heights are going to be things like square root of 3 over 2 or square root of 2 over 2 or a half. It's going to be a lot uglier. So in red, I'll do the ones that use the reference triangles. So 30 degrees, here's 30 degrees. We're doing the sine, SOHCAHTOA, so sine is opposite over hypotenuse. The opposite is 1, hypotenuse is 2. So the sine of 30 degrees is 1 over 2, it's a half. So 1/2. Next up is 45 degrees. 45 degrees uses the other triangle. That was the word problem. That was earlier notes. I minimized too much. There we go. So we're doing the sine of 45 degrees. Here's our 45, or the other one if you want. Opposite is 1, hypotenuse is square root of 2. So that's 1 over square root of 2. But I'm not going to write it that way. I'm going to write it the way you've already seen several times. Oh, mailman, sorry for the distraction. Or FedEx man, more specifically, or woman, didn't see the person. I keep going to the wrong document. It threw me off. Yeah, here. So this was 1 over square root of 2, but we've seen this enough to know that you multiply top and bottom by square root of 2 over square root of 2, and you end up with square root of 2 over 2. Again, the 1 over square root of 2, I'm only going to show this one time, and I'm going to erase it. We multiply top and bottom by square root of 2 to get the square root of 2 over 2. You have to have these answers rationalized in the bottom. There we go. Next up, 60 degrees. 60 degrees is right here. Sine is opposite over hypotenuse. The opposite is the square root of 3. The hypotenuse is the 2. So that's our sine, square root of 3 over 2. Wrong one again. Dang it. Square root of 3 over 2. these three red numbers are going to be the same red numbers here, maybe not in that order, same numbers here, the same numbers here, but with sign differences and in different orders. And I'm gonna give you a really good way as to how you can kind of remember this. Some people would call it memorization. I call it rationalization because there's a little logic to it. It's a little leap of faith, but there's logic to it at least. All right, so we go from 0, a half, square root of 2 over 2, square root of 3 over 2 up to 1. What are these square root of 2 and square root of 3 over 2? What are those as decimals? Let's just see it because it's interesting. Square root of 2, close your parentheses, divided by 2, is 0.707. Square root of 3 over 2, close your parentheses, divided by 2, is 0.866. So about 0.7 and 0.87. You know, call it 0.9 if you want, just to round to the nearest tenth. It's not a great way of doing it, but what I'm saying is this is 0, this is 0.5, this is about 0.7, this is about 0.9, and then 1. We are going from 0 to 1. What's going to happen between 90 and 180 degrees? Our y values went from 0 to 1. They're going from 1 back to 0. We're going to scale down. We're going to go back to the 0.9. This is what you're going to end up seeing. Then the 0.7, then the 0.5, and then the 0. And then we're going to go from 0 to -1. You're going to see the same pattern of numbers repeated in a decreasing order, but negative. And then they'll increase back up to 0. So this is a good way of, you know, quickly putting things into place if you don't want to take this super long time to establish things. But let's not cheat the system. Let's go full brass tacks. Now we're going to do the sine of 120 degrees. I'm going to need to start showing some work. The sine of 120 degrees, since 120 is in quadrant 2, this would be 120. That means you have a reference angle of 60 degrees. 180 minus 120 is 60. So the sine of 120 degrees is the same thing as the plus or minus sine of 60 degrees. That's the reference angle. Which one in particular? Well, it's going to be positive because we're in quadrant 2. A smart trig class says sine is positive in quadrant 2. You choose the positive one. Sine of 60 degrees is staring us in the face. I'm not going to keep going back to that other page anymore. So this would be the square root of 3 over 2, which was the 0.9. I predicted it exactly, didn't I? So I bet you can guess that this one's going to be square root of 2 over 2 since that was the 0.7-ish. Let's confirm it though. How about the sine of 135 degrees? Well, 135 is in quadrant 2. So here's your 135. Sorry, this is all small, but I got to write a lot. Then that means that this reference angle ends up being 45, 180 minus 135. So this is equal to plus or one or the other minus the sine of 45 degrees. We're still in quadrant 2, so it's still the positive one. And we know the sine of 45 degrees, it's right here. It's the square root of 2 over 2. We don't need to re-show all that work. And you don't have to show yourself rationalizing denominators all the time if you establish and memorize. So as predicted, it was that 0.7 and some change number. Patterns, they're a thing. So I bet you can guess that the next one is 1/2. Let's establish it. The sine of 150 degrees would be the plus or minus. So still in quadrant 2, here's 150. Which says the reference angle has to be 30 degrees, 180 minus 150. So the sine of 150 is basically the same as the sine of 30, possibly negative. We're in quadrant 2, so it's still the positive one though. Sine of 30 degrees was 1/2. Boom. Next up, we got the sine of 210. How are we on time? 15, okay. Sine of 210 degrees. Well, that's going to be plus or minus the sine of its reference angle. 210's in quadrant 3 down here somewhere. So there's your 210 degrees. I'm going to draw the reference angle in a different color now because of the overlapping, which says this is the reference angle, not this one, not this one. That would be wrong. Remember, swaying your reference angle from the x-axis. That would have to be 30 degrees. 180, I'm sorry, 210 minus 180 would give you 30. Remember, the goal is to get an answer in that 0 to 90 range. So the sine of 210 is plus or minus the sine of 30 degrees, but we're in quadrant 3. A smart trig class says that cosine's positive in quadrant 3, which means sine's negative. So it's the negative sine of 30 degrees. We know sine of 30 is a half, so just slap a negative on it. This is negative 1/2. I will not do this for every single one of the rest of them. I'm going to try and we've established a pattern here. So I bet you can guess that the next one, if this is a half, it's probably going to be square root of 2 over 2 and then square root of 3 over 2, correct? Question mark? No, it's not correct. It's close. It's very close. None of the numbers I've written are wrong, but I didn't write them as negative. Negative square root of 2 over 2. I didn't leave myself enough space, otherwise I wouldn't erase that. And negative square root of 3 over 2. Don't believe me? Sine of 225 degrees is plus or minus the sine of, let's see if we can get a reference angle. You can probably figure it out based on patterns and such by now, but if not, that's okay. You can always show all your work. That's 225, which puts our reference angle as just this little bit. 180 and 225 subtracted in the appropriate order gives us positive 45 degrees. So there's our reference angle. We just said that sine is negative in quadrant 3, so pick the negative. You could have saved yourself a step of writing if you remembered that. I'm being meticulous. The sine of 45 degrees was the square root of 2 over 2. So this is negative square root of 2 over 2, as predicted. So I'm going to skip the work for the 240 degrees. I would like you to prove that it is negative square root of 3 over 2 on your own time. That would be an excellent exercise for yourself. I'm not asking for you to show me that. I'm just saying it would be good practice for yourself. But it will end up establishing that. Your reference angle ends up being 60 degrees. 60 degrees in a sine is square root of 3 over 2, but it'll be negative because you're in quadrant 3. I will do the 300, but I'll skip the next two after that because we can probably get the pattern and establish the rest. So the sine of 300 degrees would be plus or minus the sine of its reference angle. To get the reference angle, 300 is in quadrant 4, so we're spinning almost all the way around. That's our 300 degrees. Reference angle swings from the x-axis, not the y-axis, so that. If this is 300, you got to do 360 minus 300, which is 60. So the sine of 300 degrees is the same as maybe plus or maybe negative the sine of 60 degrees. Well, 300 degrees is in quadrant 4. A smart trig class says cosine's negative in positive in quadrant 4. I think I said something wrong earlier. I think I said that tangent. I meant to say tangent. I said cosine for this one, but I still had the right answer. Quadrant 3, tangent's positive, all others are negative, which is why we were choosing negative for quadrant 3. Quadrant 4, a smart trig class says cosine is positive in quadrant 4, all others are negative. So sine of 300 is the negative sine of 60 degrees. Well, sine of 60 we established was the square root of 3 over 2, so this should be negative square root of 3 over 2. Negative square root of 3 over 2. The pattern says the next one's going to be negative square root of 2 over 2. I mean, all the ones that have 5s tend to be the ones that are 45, right? I feel like that's pretty logical. And the 45 is based off square root of 2 over 2. It's just a matter whether it's positive or negative. Quadrant 4 angles, negative for sine. And then 330 would be negative 1/2 because the reference angle would be 30 degrees. Sine of 30 is a half. Quadrant 4, though, so negative. There are our 17 points that we need to make a graph with. Oh boy. All right, 10 minutes. I am going to try and copy paste this just to have it all. There we go. Okay. Ooh, that didn't work, did it? See, that when you try and move things manually like that, that's when things go wrong. That, I just want this a little higher, please and thank you. Oh well, I give up. Good enough. There's our table of values. So now we actually go to make our graph. So I don't have any negative angles, so you're going to see that I draw this as a very heavy right-sided graph. So here is x, which is our angle, and here is y, which was the sine of the angle. I'm not saying y times sine of x, I'm saying that's what it's referring to. So the horizontal is the angle, the vertical is the sine of the angle, the ratio of its opposite to its hypotenuse. The largest value out of all of this is a positive 1, the smallest value is a negative 1. So let me make the highest heights of this a 1. Let me try and make this the same distance. This is gonna go, I've never had to do this with my tablet yet, so I'm hoping I can do this as best as possible. Let's try and get a good division of this by saying, all right, the 360 degrees is the largest we're going to, so let's make this 360 degrees. The middle one is 180 degrees. This looks like about halfway, as best as I can approximate it. Might be a little right heavy, but that's not the end of the world. So here's 180 degrees. Halfway between 0 and 180 would be our 90. Halfway between 180 and 360 would be our 270. But then we got to put the 30, 45, 60, all those others in. And it's not just going to be boom, boom, boom. It's not going to be an even division. It's not going to look like that. These are actually clustered. 45 is halfway between 0 and 90, so this right here would be the 45 degrees. But the distance, this right here would be 22 and a half. We're supposed to have 30, so 30 can't go there. It needs to be squeezed in a little more. And the same idea for the 60. It needs to be a little closer to the 45. So it ends up looking something like this, where these three are kind of clustered and there's gaps. I'm going to choose a different ink color for those. So this was 30 degrees and this was 60 degrees. And the 45 degrees was the main one. Boop. All right, so next up, between the 90 and the 180, we got our 120, 135, and 150. 135 is the halfway between, so this should be about 135 degrees. And then kind of cluster them the same fashion, like so. So that'll be our 120, and this will be our 150. Halfway between 180 and 270 would be the 225. Then cluster them around that for the 210 and the 240. Halfway between 270 and 360 is the 315. Then clustered around that, cluster, would be the 300 degrees and the 330 degrees. If you can make this big enough to not have to have these all weirdly spaced, and by weirdly I mean the orange number versus the black number, if you can have them exactly aligned, that'd be great. But I can't make this big enough and be able to show everything all at once. Not with my handwriting. And let's do the graph in red. So the graph's going to be in red. So the coordinates are read vertically. So this is a coordinate, 0, 0, 0 degrees, 0 up or down. That's right here. In fact, I'm going to go ahead and do the blue ones first. So I'm going to do the 90 degrees and 1 next. So we're going to go right 90 and up 1. Then I'm going to do the 180 and the 0. So we go right 180 degrees and up or down nothing. Then I'm going to do the 270 and the -1. So 270 and -1, we go right 270 degrees down 1. And then finally the 360 degrees and 0. So we go right 360 degrees, up or down nothing. These 5 red points are what you will be doing on your own. Those are the quadrantals. But if you only do those, this is what you might think originally. You might think that the graph is just like this, like a V wave or a square wave well, that's not a square wave, just a V wave. But that's not what it looks like. Usually in math, things curve, they bend. And when you put in these red numbers, which are still going to be red points, that'll confirm the bending. So these heights, 1 over 2, square root of 2 over 2, square root of 3 over 2, that's a 0.5 roughly, a 0.7 roughly, and like a 0.9 roughly. So I'm going to need those labeled as well as I can. So here's our 1/2. Then in orange, I'm going to do the square root of 2 over 2, which is like 0.7, not 0.75, so not exactly halfway between these, just a little lower. So we'll have that be the square root of 2 over 2. And then 0.9 will be a little closer to 1, actually. Like that, maybe. And that'll be our square root of 3 over 2. Same thing on the below. We'll have the 1/2 is halfway between 0 and -1, but it's -1/2 now. Then we'll have the negative square root of 2 over 2, just a little less than halfway between those. And then the negative square root of 3 over 2, about there. All right, graph in blue. Oh, red for the points though, sorry. So 30 degrees, comma half, right 30, up a half, boom. 45 degrees, square root of 2 over 2, boom. 60 degrees, and then square root of 3 over 2, boom. This looks like a straight line here, but because of the bigger gap here and the smaller gap here, that's what causes it to do this. Now I'm going to erase it after I do this because I want to do it all at once, but this is the type of picture you end up getting ultimately. It kind of bends. All right, let's get the full picture. Then from there, we're going to start bending down. So 120 degrees is the height of square root of 3 over 2, so about here. Then 135 had that square root of 2 over 2 height. 150 degrees had the height of a half. There we go. And then we're here for the 180. 210 was a -1/2 of a height, so about here. Does that look good? That looks good enough for government work. Then 225 is the next lower one. 240 is the next lower one. I have my degrees just a little too far left on that one. That's okay. So my image isn't going to look perfect over those dots, but you get the idea based on the first one. This first one's really good. The second one, not so much. And that's why I don't suggest you ever do a 17-point approach for an actual problem. Unless you're going to ruler out everything, this can look funky. And then the same idea coming back up from 270, 300 degrees, your height was the negative square root of 3 over 2. At 315, our height was the negative square root of 2 over 2. And then 330 was the -1/2. That one actually looks pretty good right there. And I can kind of see these points are just a little high. I'm going to use those other, I said erase. I'm just going to try and kind of mimic the heights just to make it look a little better. That looks a little better. So when you connect all your dots, a nice smooth curve-like fashion. Sorry if there's little bumps along the way. I don't want to draw this in one move. I'll never get it right. See, that one wasn't perfect. Let's try again. Awful. I'm telling you, doing this blind is a challenge. So that red dot's just a little far to the left for my taste. I'm just gonna fudge it a little. It's okay, nothing wrong with that. And then here, you get that same shape, it's just upside down. So something like this, steeper at first and then flattens out, flat, and gets steeper and steeper and steeper. Oops, that was bad. There we go. That is one wave of a sine function. You know why we call it wave? Because it looks like a wave. You know those things in the ocean? They kind of act like sine waves. You know the things you hear? You don't hear them as waves. You can't visually see that, but they're waves. You know the light you see, the way you can see everything, light travels in waves. This is the shape that light, sound, water, moving, all travels. Giant, freaking giant field of mathematics. So again, this is not how we will do things, which we are out of time now. So I already introduced it, but your graph, and this is where we'll start in class next time, you would just plot this point, this point, this point, this point, and this point, and then make the shape from that. So you would just have, you plot your 0, your 1, your 0, your -1, your 0, and then you make a nice pretty wave because you've established the shape. Now in my math lab, your homework makes that shape automatically for you, which is a bit too easy in my opinion, but you still should be able to do this by hand. I am considering maybe 1 or 2 questions that I grade by hand for the first test. I'm not guaranteeing it, but I'm considering it. So we will get into this and actually establish things like amplitude, period, phase shift, and all that stuff next time. We have only just begun. We have only just established the picture that we'll be using.
Sorry, the usual video combining right there. Yes, the screen was frozen and everything. And we're just going to pick up right where we left off.
Back to where we left off, 5.5, the actual graphs of sine and cosine functions. So we started graphing the sine function. We started graphing it in a very time-consuming way where we plotted 17 points of this graph, and then once we got to 360 degrees, we know by the periodic nature of a sine function that it's just going to be the same shape over and over and over. There's a lot of work down here showing how we got that. If you did not watch last lecture, you're being a bad student. You need to go back and watch last lecture because I'm not going to do it twice. It's a lot of work. So this was graphing y equals sine of x. So x is what we call the angle, so 30 degrees, the 45 degrees, the 60 degrees, the 90 degrees, whatever, or in radians, doesn't matter. And then y would be the, well, it's coincidentally the y coordinate of the unit circle, or, you know, whatever, using the reference triangles in the red, the unit circle is what we use to get the blues, however you go about doing that. So after you get all these points, we noticed that there was a pattern with them. Every 90 degrees, they tend to be going up, then back down, down, then back up. And we got a picture that looked like, so here's same table of values. We got this picture. And what I said is out of these 17 points, we're only going to focus on 5 of them. And those 5 are conveniently the quadrantals. What's convenient about them? Well, it makes it easy to divide this thing up in 90-degree intervals. It's also easy because the heights are 0, 1, or -1, not these not randomly seeming irrational values of square root of 2 over 2, square root of 3 over 2, or the single rational value of half. So all we do is we take those 5 points, and that's how we're going to plot them. Now, I didn't finish doing this. I didn't put any of the labels on here yet, because we ran out of time. But again, x-axis, y-axis. And then we would just need to label the degree amounts on the x-axis. So the 90 degrees, the 180 degrees, the 270 degrees, the 360 degrees. And of course, 0 for the very first one. And then the heights of 1, 0, again, you don't need to label 0 ever, and -1. That's all you have to label. Now, doing this by hand, if this was a handwritten test, if you forget to write the degrees, it's wrong. If you don't write these height marks, it's wrong. Because maybe the heights aren't 1s, maybe they're 2s or 5s. Maybe this thing is doing a full wave by the 180 degrees, because we can throw in extra numbers into y equals sine of x, We can make it like y equals sine of x plus pi, or y equals 2 sine of x, or y equals 3 sine of parentheses, I don't know, 2x minus pi, close parentheses, and then a plus 7 outside just for fun as well. So back in pre-calc 1, we studied the idea of vertical and horizontal shifts as well as reflections. And those concepts are going to follow into this series of trigonometric functions. But we give them different unique names. We talk about things like amplitude, period, and phase shift. Some people just say shift instead of phase shift. But again, this is what we're basing everything on. This is, again, one wave. Now, handwritten tests, this is my favorite thing to ask for, just one wave of something. When you're testing in my math lab, they tend to give you either multiple choices with multiple waves, or ask you to type in the amplitude, period, shift, and then confirm that the picture is looking correct. So the way I'm doing things in our class is a much more traditional way, which you are supposed to be able to do and understand, because when you go into calculus, if you have to do something like this, they're going to be expecting you to do it this way. It's just the homework tests you on a slightly easier method, fortunately for your grade, unfortunately for terms of understanding. So make sure you can regurgitate with any problem the way I am doing it in class. Okay. So again, these waves, what they really look like is they go on forever and ever and ever. All I'm showing so far is just one waveform, and these might not be perfectly symmetrical because I'm, again, using a tablet that I'm flying blind with, essentially. So they started out a little wider and got a little narrower. But it's just the same wave over and over and over. I could keep going, same heights, same distances to get to the next crest or trough or what peak or valley, whatever you want to call them. All right, so for y, lowercase y, equals capital A times sine of bx. The period is, and we use the letter P to denote period, P, capital P, equals 2 pi, 2 times pi, over the B. Sorry, I gotta clear my throat. Give me a second. Okay. So what this B in here does, I hit blue. I know I hit blue. What this B in here does, basically, it's the speed of the wave. So the bigger that number is, the more waves you would get in 360 degrees. For instance, if this was a 2, what would happen is you would actually go up to 1 and back down to 0 by the time you hit 90 degrees. And then you go down to -1 and back up to 0 by 180 degrees. This blue one right here, and I'm going to erase this, I'm just giving you an idea. That's y equals the sine of 2x. It's making it go twice as fast. So it completes 2 waves. So you could get another wave here by the time you get 1. There's 2 waves in the same distance. It was 1 wave previously. So if that was a 3 there, that means you would get 3 waves in this distance. If that was a 10, that means you'd get 10 of these waves in that distance. There we go. So a period is how long it takes for you to get that full wave. So this one, the one we have in black, that full period is 360 degrees or 2 pi. We tend to talk about these values in terms of radians and not degrees. So you're going to see me using radians much more often than degrees for this because of that fact. So we got 1 full wave. A wave is going up and coming down and back to where we started. So we got a full wave in 2 pi in 360 degrees because the B here is 1. This was y, oops, wrong color. this was y equals sine of 1x. There's a little 1 that's imaginarily there, implicitly there, if you will. So that says that one wave will happen in 2 pi, because 2 pi divided by 1 is 2 pi. So understanding the period of these waves is extremely important. For y equals a equals, not minus, times the sine of parentheses, capital BX minus C. Please notice that's a minus. That is very important. Let's ignore that. Ignore that. So for this, the period is still 2 pi. The period is still 2 pi. The period is still 2 pi. But we have now introduced a new element. That minus C is what's going to be a phase shift or just a shift. So this shifts the starting point right, specifically B over C. And again, some people would instead refer to this as a phase shift. It puts it out of phase with the original wave. So when there is a plus or a minus number inside of the parentheses of your trig function, that's going to make your wave move left or right. So if you remember transformations back in pre-calc 1, which if you had me, I told you in that class, it doesn't go away. This is it not going away, it's coming back. The shifts are the opposite sign as to what you see. So minuses are pluses, pluses are minuses for horizontal shifts. So this minus, a lot of people will think it makes it move left, but it actually makes it move right. So be careful there. And then, and how much do I have? How much space do I have? I just want to make sure I got enough. Then, just an asterisk, if it was a sine of bx plus c, it would shift left instead. Alternatively, you can set the inside equal to 0 to find the shift. The shift. So some people just prefer memorizing that fraction of c over b. Some people prefer setting the inside equal to 0 and solving. It doesn't matter, they are the same thing. Some people like memorization of patterns, some people like logic and reasoning, but setting the inside equal to 0 is what will give you the starting point of your wave for the initial wave. All right, so with the amplitude, which is A, period, and the shift, you then need to find the 5 critical points to graph. So I said that we're going to boil all of these sine and cosine graphs down to 5 points. Now the sine points and the cosine points are different. This is just the graph of a sine wave. A cosine wave will look different for one wave of it. When you graph multiple waves, they basically look the same, just out of phase, as we will see. So there's a few features you need. A, which is the amplitude. Now, I actually need to specify that a little more. It's not just A, it's the absolute value of A. Because the original A could be negative. But the amplitude is the absolute value of A. The amplitude is the highest high or the lowest low of the wave. So this has a 1 in front of the sine, which is why it goes up to a height of 1 and down to a height of -1. If there was a 2 in front of it, then it would go up to a height of 2 and down to a height of -2. So different numbers in different places affect things differently. When I put that 2 in front of the x, it made us get 2 waves in the 360-degree period. When I put the 2 in front of the sine, it makes the wave be taller and lower, I guess. I don't have the word for taller, just well, taller in general. So on one single graph, after a couple examples, I'm going to paint all of those together so you've got a good idea of different causes and effects, but it's all been laid out already. So you'll need your 5 critical points, the one that's normally your 0, 90, 180, 270, and 360. But here's the thing, they aren't always those degrees. If there's shifts, they're going to be at different degrees. They're going to be at different degrees. If the period is longer or shorter, they will be at different points. They'll be at different degrees. So your first point, that's the C over B. Whether it shifts left or right is based on the middle term's sign, actually technically ending term's sign. So it's just C over B. Maybe it's moved right, maybe it's moved left. It depends on whether it was a minus or a plus. So that's your first point. So the phase shift value is also your first point for your initial wave. Then what you're going to do, then divide period by 4. This is the value that you will add to the first point 4 times to get points 2, through 5. So your first point will be C over B. It's not always starting at the origin. Maybe it starts at 90 degrees. Your second point, what you do is you take your period and you divide it by 4. Why 4? Well, here's the reason why. This graph is basically divided into 4 segments. So you have your first point. Dividing your period into fourths means you'll go 1/4 of the period to get to this point, then another 1/4 of the period to get to this point, another 1/4 of the period to get to this point, and then another 1/4 of the period to get to this point. Now, they don't have to be always increasing by 90 degrees. If your period is just maybe 10 degrees, that means you'll be going 2.5 degrees to get to the second, third, fourth, and fifth points. Because 10 divided by 4 is 2.5. So you'd start at the first one, then you'd add 2.5 to get the second, add 2.5 to get the third, add. So that's how we get the x values, the different angles. What do you do once you have the angles? You plug in these x values, which are angles, to the equation to find the y values, which are going to be, in general, 0, a, or negative a. That right there is a massive, I don't even want to say it's a hint, it's almost like a cheat. If you do enough of these, you'll be able to skip half of the work. And the half of the work you get to skip is the plugging in of the angles to find the output. Because that work very often can take a lot of time. And if you can just remember that the pattern tends to go 0, the highest one, 0, the lowest one, then 0, unless there is a reflection involved, then you can just shortcut yourself a lot of work. I know I'm throwing a lot at you all at once. We're going to practice several of these. We're going to do, what, at least 4 or 5. Well, by the time we do sines and cosines. So when you get your original thing, they ask you to graph. Write down what the A, B, and C are, because those numbers are all important. A, when you take its absolute value, is the amplitude. It gives you the heights of the peaks and valleys. B will give you the number to divide by for the period. So the bigger B is, the quicker this thing is moving, which means the period is shorter, because the period is how much degree time it takes to make a full wave. So if B is really big, you're going to make P very small. Maybe you can get 10 or 12 or 50 or 1,000 waves in 360-degree window. And then C is what causes a shift. Remember that your shifts are backwards. I did give you the 2 different ways you could find that shift. Use whichever one you prefer. And the shift also gives you your very first point. To find the 2nd through 5th points, you take the period and divide it by 4. So the 4 things you need are A, B, C, and then to divide the period by 4. All right, so with all that in mind, after like a full day of just explaining the setup of this, example 1, graph A. And we're gonna have, let me just pull back some, y equals sine of 2x. We have already actually explained and graphed this one, but let's do the full detail. Let's take our time, make sure everybody can follow along. So here's what I suggest you do. The first thing you do is you write down, what is your A, what is your B, what is your C. A is the number in front of the trig function, it's a 1. The B is the number in front of the variable, it's a 2. There is no number being added or subtracted inside of it, so that's a 0 for the C. Because of these 3 numbers, that makes the amplitude equal to 1. It's the absolute value of A, which just happens to be the same number. If the A had been -1, the amplitude would be +1 though. The period, this is where we take the period of the regular sine function, which was 2 pi, but then we divide it by this thing that governs the speed. That's the idea. The period of a sine function is 2 pi, and we take that and divide it by the thing that makes it move faster. The thing that makes it move faster is the number in front of the variable. And 2 pi divided by 2 happens to be pi. Because C is 0, there is no shift. Remember, we're supposed to do C over B, or taking the inside and setting it equal to 0. If you set the inside of 2x equal to 0, you'll get x equals 0, saying that the first point starts at 0 degrees or 0 radians. Now again, I'm going to be doing everything in terms of radians for this. It is much more traditionally done that way. Otherwise, this period I would need to write 360 degrees divided by 2, and then it would be 180 degrees. Don't mix and match your notations. It's just not a great idea. All right, so no shift. The last thing that we need to know is, all right, well, this is going to be our first point. 0 will be our first point, 0 degrees, 0 radians. But we need to find all 5 of those critical points. So what we do is we take the first point, which was 0, and then we're going to add this period divided by 4. So we don't just need the period, we also need to take the period and divide it by 4. So the period divided by 4 is equal to, well, the period was pi, not 2 pi, it's pi, and then divided by 4. This is what you add to get 0.2, 0.3, 0.4, and 0.5. So we start at 0, then we'll add pi over 4. Then we'll do it again, then we'll do it again, and then we'll do it again. And those results would be our 5 inputs, or 5 x values. So 0.1, and let me say x1 instead of 0.1 because I'm only giving you the x values. x1 is again the fact that there's no shift makes it 0 radians. x2, we take the first one and we're going to add whatever the period divided by 4 was. See, it's not just the period that you need, it's you need to slice it 4 ways because that's what gives us the 2nd, 3rd, 4th, and 5th points. So we're going to add pi over 4. I'm going to actually put that in red so you can tell why I did that. 0 plus pi over 4 is pi over 4. The third input, the third angle, we take the previous one, which was pi over 4, So this was the previous one. And then we add that number we're supposed to add again. So we add pi over 4 again. Which, that's 1 plus 1, which is 2. So 2 pi over 4, but that reduces to pi over 2. So that's our third x value. The fourth x value, we take the last one, which was pi over 2, and we add the add number again, which is pi over 4. Now, unfortunately, what I have here is something that needs an LCD. I've tried to warn you LCDs never go away. Here's it never going away. Well, pi over 2, we already had the non-reduced version of it with the same denominator, 2 pi over 4. So the cool thing is this time you don't even need to think about it. It's staring you in the face. Pi over 2 is 2 pi over 4 plus our pi over 4. 2 plus 1 is 3. So that's 3 pi over 4. Finally, the fifth point, we take the previous one of 3 pi over 4, and we add the period over 4 again, which was pi over 4. 3 plus 1 is 4, so that's 4 pi over 4, which is pi. So the amount of arithmetic you have to show here is completely up to your skill level. Some people won't show that work at all because they're amazing at fractions. Some people need to show even more detail than what I've just done. Some people just stop doing this problem because they saw a fraction and they're going to hide. You cannot be that person at this level. Fractions are never going to go away. So here is what we can do so far. We can make a table of values, and I'm going to stick to horizontal. Remember, x is the angle, y is the output. What we have so far, we're using the x1, x2, x3, x4, and x5. So 0, x2 was the red pi over 4. Not that the color matters, just giving you emphasis. The third one was the pi over 2. That's 0, 45, and 90 in terms of degrees. The third one was 3 pi over 4. And the last one was pi. So 0, 45, 90. What did I say wrong? I'm sorry, I feel like I said something wrong a minute ago. Maybe I did, maybe I didn't. 0, 45 degrees, 90 degrees, 135 degrees, 180 degrees. So this is half of the circle. We're going halfway around, whereas originally we went the full way around from 0 to 360, or 0 to 2 pi. But this is telling me that that whole wave is going to happen between 0 and 180 degrees. Now these outputs, I kind of gave you a hint here, where after we plug in these values, the y values are going to be 0, the amplitude, or the negative of the amplitude when you're done. So that idea, if you memorize which one should be the positive, which one should be the negative, watching out for reflections, if you're going to do that, we will see one of those, spoiler alerts, then you can kind of just go ahead and say, I know that this is going to be a 1, a 0, you know, something like that. I'm not saying that's right, I'm saying that you could make that idea. So let's plug these in. Let's do the 0. So the first one, where do I want to show my work? I'll show it over here. So let's do that work in orange. So plugging in the first, y equals sine of 2 times 0, which is the sine of 0. And the sine of 0, that's the y value at 0 degrees or 0 radians, which is 0. I did not pull up my board notes, did I? Let's do that. So 0 radians, 0 degrees. Remember that sine takes the y coordinate. The y coordinate is 0. So that's how I knew that this was a 0. So that's what goes here. For the second, we got y equals sine of 2 times pi over 4. The 2 and the 4 will reduce. So that's the sine of pi over 2. Sine of pi over 2, we go back to our unit circle. Unit circle. So that's 90 degrees. Sine is the y coordinate, so it's supposed to be 1. 1. Oh, look at that, a 0 and then the amplitude. For the third point, we're going y equals, let me put that third, erase, you silly goose. Third, there we go, y equals sine of 2 times pi over 2. The 2's will cancel, and you just get the sine of pi, which is 180 degrees. Sine of 180 degrees. 180 degrees is right here, y coordinate 0, so the sine is 0. For the fourth, we get y equals the sine of 2 times 3 pi over 4, which will be the sine of the 2 and the 4 will reduce to a 1 and a 2, which will give us the sine of 3 pi over 2, which is 270 degrees. 270 degrees is the bottom point on the unit circle, 0, -1. Sine is the y value, so it's -1. Look at that, the negative amplitude. Fifth and final point, now for any of these trig functions, these sines and cosines, the first and the last should be where the period is coming full circle, so to speak. So it should be the same as the 0, but let's prove it. Y equals the sine of 2 times pi, which is the sine of, well, 2 pi. And 2 pi is 0 degrees, 0 radians, so it's 0. 0, 1, 0, -1, 0. It goes 0, amplitude, 0, negative amplitude, 0. The negatives could flip-flop. And let me show you when that'll happen. If this original problem was a minus out in front with the amplitude value, then these two signs, the pluses and minuses, when I say signs there, would swap. The zeros would be in the same position. Sine graphs always go 0, first, third, and fifth, every single time, as long as there's no vertical shift, which we don't test on in this class. The sine graphs always have 0 as the anchors and the middle. And then it's just these values of the amplitude and the negative amplitude, you just got to get them right. Check this out. Undo that negative. After you plug in these unique inputs of 0, 45, 90, 135, and 180, when you do all of the math in here inside of the trig function, look at what these 5 angles turned out to be, because spoiler alerts, this will happen 100% of the time if you're following my method. We get the same 5 original inputs for the 5-point graph that have the zeros and the amplitude heights, 1 and -1. That will happen 100% of the time. So this is another shortcut you can take. If you do enough of these and remember that, hey, I'm always going to get to this after I plug everything in, as long as you don't make mistakes finding your x values, you know that you can skip pretty much every single bit of this orange work, depending on how much practice you have, how much you've memorized, how much you understand. Me, once I have these 5 x values, I can go straight to these y values. I don't need to do a single bit of this work. However, the work can confirm it. Now, do you think the first time I did it that was true? Absolutely not. I had to do it 10 or 15 times to get to that point. And the same will be true for you, most likely. But it's something that once you get to the test, it gives you a way to get things done quicker to focus on other ideas. All right. So we still haven't graphed it, have we? Let's get the graph. Yeah, we can squeeze it in. We'll do it right here. So here's our x-axis, which is our angle. Here's our y-axis, which is the output of the trig function. And then the 5 x values that I need to label are 0, pi over 4, pi over 2, 3 pi over 4, and pi. So let's just make this far right side pi. I'll make the halfway point pi over 2. Halfway between that one and the far left would be our pi over 4. And then halfway here on the other side would be our 3 pi over 4. We have heights of 1 and -1. Let's try and make sure these are spaced about the same. I'll do my points in blue. So 0, 0 is right here. Pi over 4, 1, that's right pi over 4 and up 1. Pi over 2, 0 is right pi over 2, up or down nothing. Third one, 3 pi over 4, -1, so we go right 3 pi over 4, down 1. And then pi comma 0 brings it back to where we started in terms of periodical idea. And then our graph, that last dot got a little massive, didn't it? Just make it a little smaller. There we go. And we can see our wave when we connect them in the shape that we become familiar with. That's just one wave, which I actually meant in the instructions to say graph one wave. Graph one wave. There we go. Now you might say, well, Mr. Beckner, do I have to graph this specific wave? Couldn't I go from pi to 2 pi and have those appropriate points? Technically, yes. But when I say graph one wave, I mean to start with the shifting value and make the full wave from there, which the shifting value was 0, so we started at the origin. And again, your homework, the graph might keep going. It might just, go to 2 pi and then to 3 pi and then to 4 pi. Your homework might feel a lot easier with all the multiple choice and just clicking and selecting of things. This is the skill you're supposed to have, exactly as I've reproduced this. Again, the orange bits, you can learn to skip and go straight to 0, 1, 0, negative 1, 0, or maybe 0, negative 1, 0, positive 1, 0. These don't have to be 1s. They could be 2s or 3s or 4s if there's an amplitude that's not 1. Spoilers for the next example. So let me show you real quick a couple of graphs all on the same one, y. So let's go from 0 to 2 pi is here. Before we get to example B, then this will be pi, which will make this pi over 2. And I'll make this 3 pi over 2. Then I want to have heights of 1 and 2, and then negative 1, negative 2. But then I'm also going to go from 0 to pi with those 4 values. So pi over 4 needs to be labeled. And then 3 pi over 4 needs to be labeled. So in blue, I'm going to do, no, I'm sorry, in black, let's do y equals sine of x. So your 5 points, 0 pi and 2 pi have the 0 heights. Then it'll be 1 and negative 1. This is going to be just a little ugly because of the placement there. And this one's going to look a lot flatter, but that's because of how I've drawn this. Because everything is relative to, well, the heights on the y scale. This right here, this black graph is literally the same graph as the big giant detailed one or the less detailed one. It just looks a little flatter because I had the 1 and the negative ones stretched out a little more. Now they're a lot lower because what I'm about to graph next is y equals 2 sine of x. So this has the same exact period. There's no number in front of the x. We have not done this example, but so you'll still have the points here, here, and here. The zeros stay the same. But because there's a 2 for the amplitude, instead of the pi over 2 and the 3 pi over 2 having heights of 1 and negative 1, they'll have heights of 2 and negative 2. So it makes the waves look taller. Or, more vertically inclined. Now in red, what I'll do, one that we just did in the last example, is y equals sine of 2x, the one that moves twice as fast. So this still had the heights of 1 and negative 1 for the max and the mins of the peaks and valleys, but everything happened by the time we got to pi. So the zeros were here, here, and here, where the amplitude values were at pi over 4, and the 3 pi over 4, which again, sorry for kind of overwriting there, but the picture is more important. There we go. So that's 3 different waves, the base wave in black, a wave that would be twice as high in blue, and a wave that moves twice as fast in red. So in the blue one, if I change the 2 to a 3, it just makes them taller and shallower. Well, that's not the right word. Deeper? Yeah, taller and deeper. In the red one, if I change that to a 3, then the wave would happen even sooner. It would be before pi. You would get a whole wave in 2 pi over 3, because that would be the 2 pi over b. What we're going to start doing next, though, is start mixing these characteristics together. Have a phase shift, have an amplitude factor, have a speed factor, the period, if you will. How are we on time? 40 minutes in. Okay. Not 40 minutes left, 40 minutes in. But just, we can make any wave. This blue wave that we drew as part of the example, in terms of just the picture, if you ignore the numbers, it looks just like this one, essentially, maybe a little less wide. But that's why I said that these numbers, all of these numbers are super important, because scale is everything. Because when you put these different types next to each other, you can see, oh, well, you can see that this is making it taller or deeper. You can see that this is making it move quicker. And that you could actually get two waves in the time of one with the red. You can get two waves in the time of one with the others. Tons and tons and tons of applications for this stuff. My favorite being music. How do you change pitch? Change the speed. All right, so that was example 1A, just making sure I did say A. B, we're going to graph y equals 3, so there's an amplitude factor in there, times the sine of x, there's no speed factor in there, minus pi. And there is a shift factor in there. Out of the gate, what should we do? Identify the A, the B, and the C. We can kind of mirror this last example. We identified the A, B, and C. So we could label the amplitude period, the shifting factor, and the number we have to add over and over and over and over and over 4 times to get full circle. And then we start finding the X values. Then we start finding the Y values. This is a complicated process, but with practice, it becomes more normalized. All right, so our A, the amplitude factor is 3. The absolute value of 3 is 3. The B is 1, so the period will be unaffected. And the C is going to be pi. Now, some people will say minus pi. Some people will say positive pi. If you go with the format I introduced earlier, I'm supposed to not write the minus here. If it was a plus, I would actually write a minus. But I don't care if you're messing up those signs as long as you get the location of the first shifted point correct. Because this is a minus, that means it's going to be shifting it right. Again, that will be 100% proven if you choose to just set the inside equal to 0. You're guaranteed to get that. But a lot of people forget that concept and just go, oh, it's C over B. All right, so since the A is 3, the amplitude is 3. Since the B is 1, the period, it's not just 1, it's 2 pi, the original period of sine, divided by the B, which is 2 pi. The shift factor is the C over the B. C is pi over B, which is 1. And again, this is shifting right, so these signs are correct. That is shifting. I like to at least point it out, though, to be meticulous, because some people get those signs wrong, the plus or minuses. That's a right shift, because this was a minus. Again, if you set the inside equal to 0, you just add pi to both sides, you get x equals pi as the shifting factor. And since that's positive, it guarantees that it's right. All right, so once we do the amplitude period shift, we still need the add, which was the period over 4. The period here was 2 pi. 2 pi over 4 reduces to pi over 2. That is what we add 1, 2, 3, 4 times to get our second, third, fourth, and fifth points. You miss any of these details, and you're probably not going to be able to accurately make this graph. So let me be consistent with my colors. I stuck to blue for this. Okay. So our first x value, our x1, is the shift factor, which was pi. That's where we will start this wave. x2, we take this value and we add the adding number, which turned out to be pi over 2. Pi plus pi over 2, you're going to need an LCD, which will be 2, because this pi is pi over 1, if you need to think about it that way. An LCD of between 1 and 2 is 2. For the first one, 1 will go into 2 twice. 2 times the 1 at the top is 2. So that makes that 2 pi over 2 plus pi over 2, which is 3 pi over 2. So that's the second point. The third point, sorry, I need to cough again. I swear I've had a cough since February. We take the previous point of 3 pi over 2, we keep building on it, and we add the adding number of pi over 2, the period over 4. Because after we do that 4 times, we'll come full period, we'll come full circle. 3 plus 1 is 4, so that's 4 pi over 2, which is 2 pi. So that's our third point. Our fourth point, we take the previous one, and we add pi over 2. Two pi over 1 becomes 4 pi over 2. Again, we're supposed to be experts at LCD stuff. Practice this 10,000 times if you have to. So that's 4 pi over 2 plus pi over 2. 4 plus 1 is 5. That's 5 pi over 2. So that's our fourth point. We just need one more. x5. Take the previous one of 5 pi over 2. And you might figure out the pattern really quickly, and that's up to you. And if you can shortcut the work, again, the amount of detail you're showing in your work is up to your skill level. Some people, every single one of these is a page long. Some people, it's 4 or 5 things because they've done it 100 times. They made sure to practice it. I wrote an equals because I got sidetracked. 5 pi over 2 plus the pi over 2. 5 plus 1 is 6. And 6 divided by 2 is 3. Here's a cool little trick. If you take the shifting value, if you then add the period, you should get the last point. Don't write that on your own notes. I'm just giving you the reference. If you take the shifting value and you add the period, remember, everything should be the same after one period. So if you take the shifting value and you add the period, you should end up at the very last point. First point, fifth point, and pi plus 2 pi is 3 pi. You can go and confirm that to the last one. If you take the starting value, I'm going to erase these circles after this, the starting value, which was no shift, so 0. If you add the period, which is pi, you'll get the fifth point, which is pi. That is an amazing self-check. That way, if you goof up your fraction math, maybe you got that the last point was 7 pi, and you go, well, pi plus 0 is not 7 pi. It says, oop, I goofed up. I need to go fix some things. All right, so we got our 5 points. We got our 5 x values, that is to say. So we can start with our table of values. We know our x values are going to be pi, then 3 pi over 2, then 2 pi, then 5 pi over 2, and then 3 pi. Again, pi, 3 pi over 2, 2 pi, 5 pi over 2, 3 pi. Those are just the x values. Now the y values, I've already said that if you practice this stuff enough, you can pretty much know this out of the gate. So I'm going to do this my shortcut way, but then I will show at least some of the algebra, some of the trigonometry. So this is the assumed form. I know sine, the first, third, and fifth, they're always zeros every single time, no matter what. The second and the fourth are always the amplitude values. So the amplitude was a 3, so one of these is a 3, the other is a -3. It always goes positive, negative, if this 3 is a positive. So with this 3 being positive, it has to go 3, and then it has to go -3. If this were a -3, these signs would swap. The reason being, putting a negative in front of this is a vertical reflection. Everything that was up is now down. Everything that is down is now up. You could still confirm all of that by showing the arithmetic, the trigonometry work, whatever you want to call it. But this will be what we get. let's show some of the work though, just to, make sure at least the first two are right. So I think I did that in orange. Yes, I did. Orange. So for the first point, we got y equals, we're plugging it in now, finally. Sine, the first difficulty was figuring out what to plug in. Then it's actually plugging in, and then times x minus pi, well, the x value is pi. So we end up subtracting the same value, pi minus pi is 0. So that's 3 times the sine of 0, which, well, sine of 0 is 0, so that's 3 times 0, which is 0. So certainly is 0. Remember, sine of the quadrantal angles takes on the y-coordinate of the unit circle. Again, I didn't show it, but I went back to, whoops, this. We were here. The y-coordinate was 0. All right, so the second one, and as I said, I'm only going to show a few of these. I'll show the first, second, and how about fourth? Y equals 3 times the sine of 3 pi over 2 minus pi, which is 3 times the sine of 3 pi over 2 minus 2 pi over 2. Sorry, that's getting a little squished. All I did was get an LCD. That's 2 pi over 2 there. 3 minus 2 is 1. So that's 3 times the sine of pi over 2. And look at this. We're still getting those quadrantals as I promised. 0, 90. The next one definitely 180 after you do the work. The sine of 90 degrees, back to the unit circle. 90 degrees is here. The y value is 1. So it's 1. 3 times 1, though, not just 1. And that's why that's a 3, not a 1. Terrible looking 3. Let's try that again. There we go. I said I'd show the fourth one. I think the work to do for the third is a little easier. So let's show the fourth. Colon not equals. Y equals 3 sine of 5 pi over 2 minus pi, which is 3 times the sine of 5 pi over 2 minus 2 pi over 2. You'll be getting a lot of LCDs. I can't emphasize that enough. 5 minus 2 is 3. So that is the 3 times the sine of 3 pi over 2. That's the 270 degrees. 270 degrees on a unit circle is down here. The y-coordinate's -1. So this is 3 times -1, which is surely -3. So I'm leaving you to fill in the blanks on the third and the fifth for the work if you feel the need to, which most of you right now should, but it should look similar, and you should ultimately get 0 on both of those. And after you simplify the inside as much as possible, for the middle point, you should have 3 times the sine of pi. And for the fifth one, you should end up with 3 times the sine of 2 pi. I guarantee it. Again, after you've simplified everything. Now we're finally ready to make our picture. These aren't short problems, which means you won't have a lot of them on a test. That is awful looking. Let's try that again. X, Y. Now our first point is not going to be here. It's not going to be there. The first point starts at pi. So we're going from pi to 3 pi. So let's go maybe about here. We'll call this pi. Call this, that looks pretty even. Maybe just a little too wide. About here. That looks better. 2 pi. And then here, that'll be our 3 pi. But we have more x values to label. We need to label the 3 pi over 2, which will be here, and the 5 pi over 2. I don't know why I labeled them so low. That's okay. Doesn't matter. And then the heights are just 3 and -3, so I don't need to label 1, 2, 3. I can just go 3, -3, like so. Do the graph in blue. This is wrong, this is wrong, this is wrong, but this is what people will do on mistake, on accident. The pi comma 0 is here. Then the other 0 is here. The other 0 is here. That's the first, third, and fifth. The second one has a height of 3. Fourth one, excuse me, has a height of -3. So here's our wave. Now, because I tried to stretch this a little vertically to emphasize the height of 3, You can see it, but if I made this height 3 and this height -3, you wouldn't see it. Again, it's all based on a sense of scale. And again, this is not how things work in my math lab. This is how you need to understand how to do things moving forward. I would highly suggest that you do the problems in my math lab by hand in this way, then do it the way that they are kind of dragging you by the nose over. Because again, a deeper understanding of this is important moving forward into calculus, and especially just for some things here and there in trigonometry as well, of course. Are we on time? 18 minutes. Okay. So there's our graph. So we've done 2 of these now. I think we can knock this third one out. Yes. C. Y equals biggest and beefiest of the sines, -5. That is a 5 there. That really doesn't look like a 5 though. There we go. Sine of 4x plus 2 pi. All right, I'm gonna go a little quicker with the setup. The a is -5. The a is negative this time. The b is +4, and the c is 2 pi, right? Question mark? Some people will say that c is 2 pi, but me personally, I prefer to write it as -2 pi because this is a plus. The shifting factor, which is everything having to do with c, is always opposite in sign. So if you wrote that as a positive, I'm not going to care as long as your graph is ultimately correct, but it might mess you up there. All right, our amplitude is then +5 because you got to do the absolute value. The period is 2 pi over b, so that's 2 pi divided by 4, which is pi over 2. Then the phase shift or shifting factor, whatever name you want to give it, that's the c over the b. C is the -2 pi because this will shift it left. And you did see that that last problem had a shift right. This is shifting right because it didn't start at the origin. That was a shifting right for our first point. This one shifts left because of the plus. So 2 pi over b is 2 pi over 4, which is -pi over 2 when you reduce it. So this is the location of the first point. This is the location of the first point that we need to plot to make one wave. But we also need to figure out what to add, which was the period over 4. The period is pi over 2, so we got to take that fraction and divide it by 4. Might actually help you to write that as divided by 4 over 1. Then write it the old school way. Excuse me, that was not right. Pi over 2, division symbol 4 over 1, because then you can write this as pi over 2 times 1 over 4. Pi, I keep looking at that 4 and trying to write a pi. The 2 and the 4 do not reduce, they stack, and you get pi over 8. That's what we're going to be adding 4 times to get points 2 through 5, excuse me. This division of fractions is not going away. You're going to see it multiple times throughout the semester. I'm a broken record, what can I say? So our first x coordinate is the shift factor. Our first x coordinate should be -pi over 2. Now just because this is negative doesn't mean we're going to subtract. That's definitely not true. We're adding the period divided by 4, which is pi over 8. So x2 would be that -pi over 2. A negative could be a little better, couldn't it? There we go. And then we're going to add the shift factor, which was the add value, pi over 8. We take the shift factor and add the adding value. Well, you're going to have to get an LCD between 2 and 8. Your LCD is 8. 2 goes into 8 4 times. 4 times -1 is -4. So this is -4 pi over 8 plus pi over 8. -4 plus 1 is -3. So -3 pi over 8 is our second point. These are definitely going to be the least pretty, but that's okay. Nothing wrong with that. So our third x value, take the last one, negative 3 pi over 8, and we're going to add the adding value of pi over 8. Negative 3 plus 1 is negative 2. That's negative 2 pi over 8, which reduces to negative pi over 4. The fourth x value, we take the previous one of negative pi over 4, and we add the adding value of pi over 8. Now, if you haven't figured this out by now, if you reduce a fraction and then end up having to add it to get an LCD, you just end up using the non-reduced version. The negative pi over 4 is negative 2 pi over 8. So you can actually borrow a lot of information sometimes. So that's negative 2 pi over 8 plus pi over 8, which is negative 1 pi over 8, but we don't write the 1. Again, there is a 1 implicitly there, but we don't write 1s in types of fractions like that, or next to variables or next to pi's, whatever. The last point. Now remember, if you take the shifting value and add the period, then you should get the last one. So the shifting value is negative pi over 2. The period is pi over 2. If you add those two things, you get 0. So that's what I expect to get here is 0. Let's take the previous one of negative pi over 8, add the adding value. Negative 1 plus 1 is 0. So sure enough, it worked. So we have our 5 x values. It is my opinion that is the most challenging part of these problems. The graph shape memorized, pretty easy. Doing enough of these that you can skip the orange work doesn't take that much time and practice as long as you are practicing appropriately. And I don't know what to say about inappropriate practice. I have some silly ideas in my head, but I'm not going to say it. All right, so not orange yet, black. So table of values, but only half of it, just the x's and the y's. We started with the shifting value, so negative pi over 2. That was the first. The second was the negative 3 pi over 8. The third is going to be the negative pi over 4. The fourth is going to be the negative pi over 8. And the fifth is going to be the 0. Now these y values, I inherently know what they're going to be. Zeros for the first, third, and fifth, because it's a sine wave. That's what they look like. Cosine waves, that's not the case. Tangent waves, definitely not the case. The reciprocal functions, also definitely not the case. We will get there. This takes a long time to set up. Then these two values are the amplitude values, which the amplitude was 5, so it either goes 5, negative 5, or negative 5, 5. Because this was a negative value, that makes it go like this, negative 5, and then positive 5. That little bit of memorization based on pattern, not just blanket memorization, saves you a lot of work. If it takes this long to do the x values, if you can save yourself some time somewhere else, that's a great idea. Because there's not really a great time-saving element otherwise to finding the x values. So if you can save time on the y values, why not do it? Definitely not going to show all this work. Let's do the first one, and that'll probably be it. So for the first, we get y equals negative 5 times the sine of parentheses. Now, it was 4x plus 2 pi. So 4 times negative pi over 2, that's the 4x, then plus 2 pi, and then we close that parentheses. So that's y equals negative 5 times the sine of, the 4 and the 2 reduce to a 2, so that'll be negative 2 pi plus 2 pi. So that's y equals negative 5 times the sine of 0, which is negative 5 times 0, which is 0. It works. So remember, after you simplify that inside as much as possible, once you are to this point, there's no pluses and minuses inside. If you're plugging in the first, it should be 0. If you're plugging in the second, it should be 90 degrees or pi over 2. If you're plugging in the third, it should be pi or 180 degrees. And then 270 or 3 pi over 2, and then 360 or 2 pi. That's why with practice and memorization, we can just go straight to the, all right, we know these are 0. 0, 0. And then if you plug in the second one, you can confirm that it goes -5 and then +5. Um, 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 um. Do you want to see? Let's do the second one. You probably need to confirm that that's negative. That would make you feel good. I know it would make me feel good showing you. So we'll do 2 and then move on. So y equals -5 times the sine. Sorry for the 5 and the s looking the same. Hopefully you get it right in your notes. And then 4 times, now we're plugging in -3 pi over 8, then plus the 2 pi. That's y equals -5 times the sine of the 4 and the 8 reduced to a 2 in the bottom. So -3 pi over 2 plus 2 pi, which is -5 times the sine of, if you get an LCD, that's going to be -3 pi over 2 plus 4 pi over 2, which is -5 times the sine of pi over 2, which is -5 times 1, which is -5. So it works. Sine of 90 degrees is pi over 2. I'm sorry, the sine of 90 degrees, which is sine of pi over 2, is +1 because the y value of 90 degrees, 0, 1, the y value is 1. So it worked. So I'll leave you to fill out the 3rd, 4th, and 5th on your own time should you want to. I would suggest it. All right, with our last 10 minutes remaining, let's develop the cosine graph. So these 3 examples were all sine, sine, sine. Everywhere is sine. I know, it's a cheesy joke. Sorry, I had to. Sine, sine, everywhere is sine. Now let's do a cosine. Let's introduce, and we're not going to do the 17 points. We're just going to do the 5-point approach and just understand that sines and cosines will do this same kind of shape. We talked about how the sine of one angle is the same as the cosine of 90 minus the angle, which right there proves that sines and cosines are literally the same thing, just out of phase with each other. The sine of x is the same thing as the cosine of 90 degrees minus x. So cosine is the same basic shape out of phase. It has a shift to it basically, but because of this minus and the 90, the shifting is too weird to do it that way. So we don't do it that way. And that minus also kind of adjusts the graph a little bit, but the same wave pattern, this shape, if you kept drawing it over and over, you wouldn't even be able to tell whether it was a sine or a cosine. So here's what we're going to do. For y equals the cosine of x, we're going straight to the 5-point approach, but only using the quadrantal. So 0, and I'll do it in degrees: 90, 180, 270, and 360. All of these outputs are going to be 1s, 0s, or -1s, spoiler alerts. But it's not going to be the same 0s on the 1st, 3rd, and 5th, also spoiler alerts. And that was degrees. So if we want to know what's the cosine of 0 degrees, so y equals the cosine of 0 degrees. Well, now instead of using, wrong one, now instead of using the y coordinate on these 4 points, we're using the x coordinates because cosine is the x coordinate on the unit circle. So for 0 degrees, it's 1 now. The cosine of 0 degrees is 1. The sine of 0 is 0. The cosine of 0 is 1. So the cosine of 0 degrees is 1. So that's a 1. Then y equals the cosine of 90 degrees, back to the unit circle. So that's the top point. X value is 0. So 0, 180 degrees. 180 degrees is right here. X value is -1. Oh, sorry for that. I hope that wasn't too loud. All right, next up, the 270. So that's the bottom point on the unit circle. Here's 270 degrees. X coordinate is 0. The 0 degrees and 360 always match, so you can pretty much guarantee this is 1. Let's just show the work anyways for good measure. So cosine of 360 degrees, 0 degrees is also 360 degrees. Its X value is the same as it was, so 1. Different patterns. The 0 is on the 2 and the 4 this time, and then your amplitude values are the 1st, 3rd, and 5th. So the amplitude versus the zeros have swapped 1st, 3rd, and 5th with 2nd and 4th. And it goes 1's on the outer, -1 on the inner. If there was a negative here, then the signs here, here, and here would all swap, as you may have predicted if you're all right with numbers. So this graph, what it ends up looking like, so we have our heights of 1 and -1. We're going to go up to 360 degrees. And again, typically we'll do this in radians. Just for the basic one, I like to use degrees. So our points, 0 degrees has a height of 1, so it's here. 90 degrees has a height of 0. 180 degrees has a height of -1, it's down here. Then 0, and then +1 again. So here's what some people might accidentally think. They'll think, do this, that what I'm doing is wrong. I'll do red for wrong. They'll do this. Oh, this just forms a V. This is a cosine wave. No. We've already said that sines and cosines have the same shape because a cosine is just at a phase from a sine and a reflection, essentially. So that was very, very wrong. Do not draw a V out of that. What you do with this V, so these cosine waves always end up looking like you would draw a V, but then you make it wavy. So because of my artistic ability, I have to draw it from the middle. So like kind of parabola there, like a parabola connecting. Ooh, that was a little ugly. Let's do that one more time. A little better, little better. There we go. Come on, connect perfect, please, and thank you. That looks like it's going up. I shouldn't do that. I'm gonna get it right this time. No, I'm not. You think it's fun doing this with the pen and paper, pencil and paper? Do it blind, and you'll understand my struggle. Here we go. So that is what a cosine wave looks like. Again, we could have taken that full 17-point approach and we would have gotten the same shape. The clustering would have proved that it bends and is not an exact V, but I just make that proof with this statement that sine and cosine are out of phase with each other, which means they have to be the same shape. Now you might say, well, Mr. Beckner, this is not the same shape versus y equals sine of x, super quick. Look like this instead. I'm not even going to put all the numbers up there, just 2 pi. Why does this isn't the same exact shape? Again, it's because you're only drawing one waveform. If you kept drawing this red shape and you kept drawing this blue shape, would you really be able to tell the difference of those? No. It's just sines without phase shifts start at the origin, whereas cosines do not. That's the one inherent difference of them. So when you only draw one waveform, which again is what I prefer people doing by hand, but not necessarily what my math lab has you do, the graph pictures do look a little more distinctive. The cosine has this shape, whereas a sine has a more traditional wave shape. So again, very important to understand the differences there. I do reserve the right to have just like a, call it a pencil paper version only of a question that won't be in my math lab, and it could be make one of these graphs in just one waveform. I could do something like that and make you attach it to your work. Whether I do or not, I haven't decided. I'm kind of leaning that way, but we'll let you know as the test details come in. But that's time for us. When we come back next time, we will do, I don't know how many, one or two of these cosine graphs, and then we'll get into the next section. So we're almost done with this section, but not quite. So that due date is on pause. So this section will be due on the 30th.
Sorry about that. All right, so again, just reminding you that we did finish 5.3 and 5.4 a while ago, so those are due on the 10th, and that we will finish 5.5 next time, and it'll be due a week from then, but please go ahead and start that homework. I got lots of questions today, which is awesome. I know this is definitely something where you have to keep things more organized, but besides that, study hard, email me if you have any questions, and we'll see you Thursday ready to pick up 5.5 and then continue into section 6. Take care.